All right, chapter 10, section 4, inscribed angles and polygons. That first term, inscribed, is going to be obviously the main focus of this section. The term inscribed literally translates as something that is written within another object. But there are lots of different ways I could have something drawn within a circle, for instance. Again, the focus of this chapter on circles, that's going to be our main focus object. And really, everything that's being covered in these sections is how different objects interact with that circle. And so in this, we're going to focus on how angles and polygons interact with that circle. And the term inscribed is how that angle or polygon will interact. So in terms of an angle, you can kind of see it here in the diagram as I've shown it. The angle is actually one of the simplest geometric shapes that there is. Okay, it's simply two segments that meet at a common point, right? And anyway, but all that has to happen for an angle to be inscribed is that the vertex of that angle needs to be on the circle. Okay, in order for it to be an inscribed angle, I just need the corner or vertex, wedge point, whatever you describe it as, I need that to be on the circle itself. If it's located anywhere else, and I kind of show you an example of something that's not inscribed, if it's, say, for instance, somewhere floating on the inside of the circle, or if the vertex is outside the circle, it's just simply not inscribed. It doesn't mean it doesn't exist or anything like that. It just means it's not this special case of an inscribed angle. And then over here on the right, I kind of break down some of our other terminology that we need to be aware of because we are getting some results that are similar to what we had in previous sections. Namely, we're getting some arcs. For instance, in this diagram, I have an inscribed angle, what we would call angle B, where the vertex or angle B is on the circle itself. And you can see it kind of breaks up the circle into several different arcs, just this angle alone. The arc that we're going to be really caring about is what we call the intercepted arc. Intercepted arc, it's just simply the arc that's going to be in the mouth of that angle, that Pac-Man mouth, or however you think about it. The intercepted arc is the arc that's inside the wedge of the angle. You're going to see another term, subtend, right? And I kind of use them in some phrasing just so you can see how it's used. It's actually far less important to like define it. Again, I'm not going to say like, hey, define what subtend means or anything like that. You're going to see it used in sentences. For the most part, it's going to make sense what it's talking about. But they're going to use the phrase, for instance, like arc AC subtends angle B. The term subtend for us just simply means it's contained within. Okay, so if I talk about angle B right here, both arc AC and chord AC are subtended within that angle. All right. And again, all it means is it's contained on the inside. Anything that's subtending, it means it's just inside the wedge. So again, not a terribly important term, but you're going to see it used, and that's just simply what it means. Okay, so again, I'm going to fundamentally get an inscribed angle and something called an intercepted arc. The focus of this front half of section 4 is basically on that relationship. And this theorem that you see at the bottom of your screen, let me move this up a little bit. This theorem becomes one of the main punchlines for this entire section, both with inscribed angles and polygons, but it comes up quite a bit. So make sure that you understand what's happening here. It's actually a very simple relationship. All right. So if I have an inscribed angle, again, all that means is that the vertex of that angle, the corner of that angle, is on the circle. Fundamentally, it's going to create an intercepted arc, like we see in the diagram up here. Inscribed angle, intercepted arc. What's the relationship between their measurements? This theorem breaks it down. The measure of an inscribed angle, which will be in degrees, it's an angle. The measure of an inscribed angle is 1/2 the measure of its intercepted arc. The measure of an inscribed angle is 1/2 the measure of its intercepted arc. So to kind of illustrate that with an example, let's say that this intercepted arc here was, say, 80 degrees. Because again, arc measurement that we covered in a previous section is measured in degrees as well, kind of telling us a portion of the slice of the whole pizza, so to speak. Right? But if I knew that this arc measurement was 80 degrees, this inscribed angle with the same endpoints as that arc would have to be 1/2 that value. So I would simply take the 80 degrees, multiply it by 1/2, or divide it by 2, whichever way gets you the same result. That would be 40 degrees. The flip side is also true. Maybe I know the angle measurement. Maybe I know that this angle measures at 36 degrees. If I wanted to know the measurement of the intercepted arc, now in that direction, I would have to multiply this by 2, double it, okay? So if I knew this was 36 degrees, I'd multiply it by 2 to find out the intercepted arc would be 72 degrees, right? So it goes both directions. And just if you want to write this in the margin, kind of a quick sanity check on how you can, because the most common mistake here is people multiply by a half when they should have multiplied by 2, or they divided by 2 when they should have multiplied by 2. Okay, the direction matters. So if you want to write it in the margin, the inscribed angle will always be smaller than the intercepted arc. Okay, the inscribed angle will always be smaller than the intercepted arc. So if you do your calculation and you accidentally ended up with a bigger number for the intercepted angle, you just probably divided, you probably multiply by 2 when you should have divided by 2. Or if you got a smaller number for your intercepted arc, you probably divided by 2 when you should have multiplied. Okay, so it's a simple relationship, but just make sure you go the right direction, because that's really where the only mistake you can make is. The inscribed angle will be half the measurement of the intercepted arc. All right, so I do in the notes, again, these are uploaded into Google Classroom. I do just a brief, fully explained example right here. So what will you see in terms of problems and big ideas and stuff? We'll work through an example in just a second. This is just a fully worked out one that I did to illustrate what's happening. You'll be given a circle, surprise, surprise, and you'll be given a series of chords, diameters, radii, whatever it might be, that are happening within that circle. We see a kind of a Z shape drawn here. So the first thing to really just get used to is being able to identify an inscribed angle. In this diagram, there are actually 2. Okay, angle R, created by QRT right here. This is an inscribed angle. And so it's important to be able to both identify the inscribed angle and its intercepted arc. So angle R, its intercepted arc created by this wedge, is arc QT. Okay, so this angle measurement, which they explicitly tell us is 50 degrees, is going to be exactly 1/2 of arc QT. So in this case, I would simply double 50 degrees to find out arc QT is 100 degrees. All right, so that's without even looking at what the question's asking for. The other inscribed angle is angle T down here. Angle T created with this wedge RTS or STR, whichever way you go. In this case, they don't tell me what the angle measurement is, the inscribed angle. They simply tell me the arc measurement. So arc RS, which is created with this inscribed angle, is measured at 48 degrees. And so in this case, I would divide this number by 2 to find out that the inscribed angle, which has to be 1/2 of it, would be 24 degrees. Okay, so just to kind of get used to how these diagrams are used, if they're showing you the inscribed angle, they're going to stick it inside the wedge right there. So nothing really surprising there. For arc measurement, they're going to show it outside of the circle like this. So just be able to interpret both. So this 48 degrees refers to the arc measurement from R to S, whereas this 50 degrees on the inside is the measurement of angle R, the inscribed angle. And again, it just gets back to that relationship described in this theorem here, that the inscribed angle is going to be 1/2 of the arc, the intercepted arc that's created. And the inscribed angle will always have to be smaller. So in this case, the 50 degrees will be smaller than the 100 degrees that is created with arc QT. This angle T has to be smaller than the 48 for its intercepted arc. So I would divide that guy by 2 to get 24. Okay. All right, so just to kind of show what kinds of questions you'll see based around it, they ask us for a measurement of angle T. In that case, again, I would just divide the intercepted arc by 2 or multiply it by 1/2, whichever way you think about it. So in that case, again, angle T is 24 degrees. In this case, they ask for measurement of minor arc QR. Now notice that QR is not technically part of either of those inscribed angles. But the way I can go about solving for it in this diagram, since RT is a diameter because it passes through center P. Since RT is a diameter, that forces this half up here to be 180 degrees at the top of the circle. And so I could use the fact that QT, arc QT, found by doubling an inscribed angle, QT is 100 degrees, so that leaves 80 degrees left over for arc QR. So that's how you can kind of connect the dots between some of the other theorems that we've done. And again, I kind of show that in the work there. Both these notes, again, are uploaded into Google Classroom, so you can upload that and if you want to kind of check out these solutions. But that's just kind of an illustration of what's happening. Okay, so that's kind of our definitions and theorem we're going to be talking about with inscribed angles. I'm going to go ahead and stop the clip right here. And in the next one, I'm going to do a single example and talk about a corollary to this theorem about inscribed angles in the next clip. It'll be pretty brief. And then after that, we'll do a clip on polygons. But I'll go ahead and stop this clip right now.